Hey everyone, so in this video we will introduce some concepts related to probability. So we'll begin by defining probability and setting up some notation for representing probabilities. We'll talk about some language related to describing random events, and then we'll introduce 4 rules for calculating probabilities, namely the addition rule, the complement rule, the general addition rule, and the multiplication rule. So let's start with the definition of probability. Probability is the proportion of times that an outcome would occur if we repeated an event many times under the same conditions. So essentially, what is the long run likelihood or the long run chance that a particular outcome would occur? We denote the probability of some event as P of E. So capital P in parentheses represents a probability. In order for probabilities to be valid, there are some limitations. Namely, any probability is bounded between 0 and 1. In order for a probability to be 0, that means that whatever event E is, it's impossible. Event E cannot occur if the probability of it is 0. Similarly, if the probability of E is 1, then whatever event E is, it's guaranteed to occur. It's really the only possible outcome. Most of the time, probabilities will range somewhere in between 0 and 1. So the way we talk about probabilities of events depends on how they're related. Very often, we want to talk about the probability of not just one event, but the probability of 2 events. Events can be what we call mutually exclusive, independent, or neither of these. Let's talk about what those mean. For mutually exclusive events, these are 2 things that cannot both happen at the same time. There's no way for them both to occur. We also refer to mutually exclusive events as disjoint events. On the other side, events that are independent can occur together and do not affect the probability that they occur. So they're independent if A does not affect B and if B does not affect A. If there is some sort of relationship between the 2 events, A and B, we refer to them as dependent events. So a probability distribution, then, is a useful tool to help us list or understand the probabilities of mutually exclusive events of a random trial. So think of a probability distribution like a list or a table or a formula that gives you the probabilities of all of the possible outcomes. Now, probability distributions themselves can be either discrete or continuous depending on the type of variable that we're considering. So categorical variables, discrete numerical variables will have discrete probability distributions. We'll chunk up the probability based on each of the outcomes. If we have a continuous random variable or a continuous numerical random variable specifically, then the probability distribution is a little bit trickier to work with. We're going to focus on discrete situations first, so probabilities related to either categorical variables or variables that are numerical discrete. So let's introduce some rules for working with probabilities. First, let's talk about the addition rule. So if any 2 events, A and B, are mutually exclusive, they cannot both occur at once, then the probability that either one occurs, the probability of A or B, is found by simply adding. We take the probability of A, add to it the probability of B. So for example, we have data that suggests that we have data that attributes a single cause of death to each death in the United States. This data shows that among people aged 15 to 24, the probability that a randomly chosen death was accidental is 0.41. The probability that it was a homicide is 0.16. And the probability that it was a suicide is 0.15. Let's find the probability that in this age range, the death is attributed to one of these 3 causes. We'll assume that these are mutually exclusive events. We're assigning a single cause of death. There's no overlap. If that's the case, we can use the addition rule and just add up these probabilities. So the probability of A or H or S is the probability of A plus the probability of H plus the probability of S. Add those together, we get 72% or 0.72. A second rule that we can use to help us find probabilities is called the complement rule. So I'm going to let A superscript C, so A with the little c up top, represent the event that A does not happen. So every event has a complement. It either occurs or it doesn't. So then the complement rule, the probability that the event does not occur, is just simply 1 minus the probability that it does. So same example. What's the probability that the death is due to some other cause? Well, I'm going to let E represent that event. Typically, we assign capital letters to represent events or outcomes just to make life a little easier when we're writing the probabilities. So let event E be the probability that the death was an accident, homicide, or suicide. Probability of E is 0.72. Probability that it was some other cause, or E complement, is a 1 minus the probability of E, 0.28. So 28% of deaths in that age range are attributable to some other cause. Now let's take a look at a more general form of the addition rule. So suppose that two events A and B are maybe not mutually exclusive. Maybe they can both happen at the same time. So the probability of A or B is then the probability of A plus the probability of B minus the probability of A and B minus the probability that they both occur. Why are we subtracting this away? Well, it turns out that if we don't, we double count that region. The probability of A and B is contained within A, but it's also contained within B. It's where those two Venn diagram circles, if you will, overlap. We don't want to double count that probability, so that's why we're subtracting the probability of A and B. So let's take a look at an example. Insulin injections and oral medication are two key options that we can use to treat patients with diabetes. The 2014 National Diabetes Statistic Report provided the breakdown of diabetes treatments among American adults with diagnosed diabetes. So we have the percent of diabetes patients who are taking insulin, that's 28.7%, oral medication, 71.6%, both insulin and oral medication is 14.7%. Neither insulin nor oral medication is 14.4%. Let's find the probability that an adult with diabetes uses either insulin or oral medication. So I'm going to let I be the event they use insulin, O be the event that they use oral medication. This both insulin and oral medication is contained in two places. It's contained in oral medication and in insulin. So in order to use the general addition rule, we have to work with it like this. We'll take the probability of I plus the probability of O minus the probability of I and O. So we get 0.287 plus 0.716 minus 0.147, 85.6% of diabetes patients use insulin or oral medication, or perhaps both. Our last rule for this video is the multiplication rule. Now this multiplication rule only applies in one situation, but if it applies, it's very useful for us. If two events are independent, that is if A and B are unrelated, then the probability that they both occur, A and B, is the probability of A times the probability of B. So we can use this rule in a couple different ways. We can use it to find the probability of A and B if we're willing to assume independence. We can also use it to verify or disprove independence. If the multiplication rule is not satisfied, then A and B cannot be independent. So for example, mandatory drug testing in the workplace is a common practice for certain professions, things like air traffic controllers, for example, or transportation workers. These are not perfect. False positives in drug screening tests do occur, and they occur when the test incorrectly indicates that a screened person has recently used illegal drugs. Suppose this mandatory drug test has a false positive rate of 1.2%. So 1.2% of people will come back The test will say they've recently used illegal drugs when they in fact have not. Given that 150 employees are in reality drug-free, what's the probability that at least one will falsely test positive? So we'll assume that these drug tests are all independent. The outcome of one has no effect on the others. I'm going to let F denote a false positive. We'd like to find the probability that there's at least one false positive in 150. This is actually going to require us to use two probability rules. So we know for a single employee, the probability of a false positive is 0.012. That means then for a single employee, the probability that the test is not a false positive is 1 minus 0.012. Assuming that these tests are independent, we can then use the multiplication rule. This rule extends all the way ad nauseum, so we can keep going. The probability that no employees have a false positive out of the 150 that are tested is 1 minus 0.012 raised to the 150th power, because we're multiplying each independent not false positive. So we get 0.163. So there's about a 16% chance that there will be no false positives. That means then by the complement rule, there's at least one false positive 84% of the time. So to get the probability that there's at least one false positive, that's the complement of no false positives. So we'll take 1 minus 0.16 to get 0.836 or 0.84%. Next example, are insulin injections and oral medication independent for treating diabetes? Let's try to use the multiplication rule to find out. So if these are independent events, then the probability that a patient uses insulin and oral medication should be the probability that they use insulin times the probability that they use oral medication. The probability of insulin and oral medication, as given in the table, is 0.147 or 14.7%. If we take the probability of insulin times the probability of oral medication, again, just pulling values from the table and multiplying, we get 0.205. These are clearly not equivalent probabilities, so these are not independent events. Whether a patient is on insulin affects the probability that they're also on oral medication, and vice versa. So that's it for our first introduction to probability. In the next video, we'll talk about a special type of probability known as conditional probability. See you then.